welcome back. In the last lecture I introduced semantic tableaux method, and using semantic tableaux method you can talk about validity of a given modal logical formula. That means when the conclusion follows from the premises, or you can say that when two groups of sentences are said to be consistent to each other, or there are many other things which you can talk about using semantic tableaux method. So in this lecture we will be considering some more examples so that you will get used to this very important technique that we employ in employ it as some kind of decision procedure method. So in the last class we have seen that if you are using semantic tableaux method, and if it is a K system, if you negate the formula that if it is necessary that P implies Q implies it is necessary that P implies it is necessary that Q, that kind of formula, if you negate the formula, you do not require to impose any constraint on the accessibility relation. That is why it is called minimal modal logical system K. In the same way, in the case of D, if you negate the formula, it is necessary that phi implies it is possible that phi. If you negate the formula and construct a tree, you require that that particular branch closes only when you invoke this serial property. Serial property is that for all x there is always some kind of world which is accessible from the world W, and in that world your formula phi is true. In the same way, T closes only when it is reflexive. That means negate the formula. If you negate the formula, it is necessary that phi implies phi. It holds only when a reflexive relation holds. So like this, if it is in S5, a formula which is in S5, it closes only when it is symmetric, reflexive and transitive. The same kind of things that Kripke talked about in terms of relational structures can be done by using semantic tableaux method. So let us consider some examples and see whether these formulas are valid or not. So we will start with the simple formula like this one. Imagine a situation that suppose if I write like this, whatever I write is considered to be a theorem. Now we are trying to check it, that is why I put question mark. Suppose if you have a formula like this, A and B implies it is possible that A and it is possible that B. So now we want to check whether this formula is valid or not. So in the semantic tableaux method, what you do is you negate the formula and start constructing the tree for this formula. So that is you take the negation of the formula, it is like this. So now this is simply x implies y, so that is why A and B and not of possibility of A and possibility of B. So you need to note that so suppose we need to mention here under what logical system you are checking this formula. So if I write K here, that means you are checking this formula in the logical system K. K does not require any constraint to be imposed on the accessibility relation. So now coming back to this one, 1, 2, so this is denial of the well formed formula, and then 3, 4 and 5. So for simplification you will get this thing. Negation of conjunction is disjunction, and it is negation of possibility of A, that means it is impossible that A, and negation of possible that B. Now so all these things are true. Let us assume that they are true in a world 0. You can take W or you can take U or you can take V also. So now A and B, so same thing, 3 is simplified into this thing, A 0 and B 0. That means A is true in a world 0, B is true in a world 0. So now negation of this one, this is it should be like this, it is a branch, so that is why we write it like this, negation of possibility of B. So this is we have this modal negation rule which we need to use. So that is whenever you have negation of possibility of A, you can simply replace it with it is necessary that not A. So this will become this, and you need to mention the worlds that they are true, otherwise it does not make any sense. In modal logic you need to talk of every formula either with respect to truth of the formula with respect to a world, truth of the formula with respect to a frame or a model or all kinds of models. So this will become not B and 0. Now, so we are trying to understand under what conditions this branch closes. So now observe here, A is true in a world 0, B is true in a world 0, but here necessity of not A is true in a world 0. So now unless and until there is a rule with which there is a T rule which tells us that if a formula is true in a world 0, then we can straight away replace it with A 0. That means necessity of A is 0 means A is true in that world itself. That means you require some kind of reflexive relation here. So once you apply the T rule, then only this closes. So A and B and everything is same. Okay. Now you can straight away replace this one with not A is 0 and not B is 0. So this then you have A 0 and B 0 and you have a literal and its negation occurs, this closes, even this closes. This formula holds in T. So now what about K? Usually it is expected that possibility of A and B need not have to be same as possibility of A and possibility of B. So let us see whether possibility of A and possibility of B leads to the other way around, converse is true or not. So in this case, at least in the case of logical system K, it is going to be invalid. But whereas in the case of only when you invoke T rule, this branch closes, otherwise the branch is going to remain open. Open branches tells us that whether the given formula holds in something or not. In K it is definitely invalid. So for the counter example, we need to draw like this. A 0 and A and B are true here, and since there is no such kind of relation, I mean suppose if you have a formula necessity of not A, there is no way in which you can move to another world. So I said in the last class that whenever you have a formula necessity of A, this does not imply that you should always go to another world, but whenever you come across a formula like this, it presupposes that you need to go to a different world and in that world A is true. But this does not give you guarantee that you should go to another world where A is true. So this is the thing which you need to note. The same type of situation arises here. So you have necessity of not A is 0, necessity of not B is 0. That does not imply that A is 0 there, unless and until you invoke T rule. T rule involves reflexivity. So unless until 0 is accessible to 0 and 0 is accessible to 0, there is no way in which you can close the branch. So the counter example can be constructed from the open branch. Suppose if you are talking about K, you are not supposed to use this T rule, so this branch ends here itself. So there is no way in which you can move further. So this itself a relational structure, this itself will serve your purpose. So there is a world, in that world both A and B are true. But it did not have to be the case that possibility of A is true, possibility of B is true. For the possibility of A to be true, there should be some kind of world which is accessible to this one, but there is no world which is accessible to this one. So that is why this formula is going to be false, and even possibility of B is also going to be false. That makes this sentence T and this as false. So that means they can construct a counter example, especially when you are talking about system K. So now what will happen if you reverse the order? So that is this one. It is possible that it is possible that A and it is possible that B. From this, let us see whether under what conditions this formula holds, A and B. So it's like it is humid and it is raining. It is possible that this is a combined sentence. It is possible that it is raining and it is humid. Does it imply that it is possible that it is raining and it is possible that it is humid? So that is the question, that is the thing which we are trying to see. If it holds, under what condition it holds. So these are the things which we are trying to see. Again this is x and not x is you negate the formula, then this is going to be like this. So this is, you put the negation inside, this is considered to be the denial of the conclusion. So now x implies y, not of x implies y is possibility of b. Now it is not possible that a and b, all these things are true in a world 0, for example. You begin with, you consider it as actual world. So now possibility of a and possibility of b can be written like this. Possibility of b true in a world 0. If you simplify this one, you will get this one, necessity of not of a and b. So now you don't have to write immediately here. If you draw a line like this and say 0, and that all the formulas that are there here are true in a world 0. Possibility of a is true in a world 0. That means you have to go to a world 1 where in that world a has to be true. Now another formula is there which is starting with the possibility operator. So now when you remove this possibility operator for the next time, which is occurring in the same branch, then you need to use another index letter. So 1 is the one which we exhausted already. So you have to go to another world other than the world 0. So now you have started from here. First time you went to this one 0 1, and now you need to go to another world 2. So now if you remove this thing, it is again you are moving from 0 to 2 now rather than 1. 1 we already gone, so you don't have to go to, you don't have to go there again. So in that thing your b has to be true in a world 2. Now we have this formula, necessity of not of a and b is true in 0. That means not of a and b has to be true in all worlds. So now first you apply this one, not a is true in a world 1, not b is true in a world 1, because not of a and b is not a or not b. So now we need to see whether literal and its negation occurs in the branch. This closes here, and now a, you have b is true in a world 2. So b is true in a world 1, b is true in a world 2, but not b is true in a world 1. It is like here b is true and not b is true here. There is no way in which you can close the branch here. So now again, once again you apply the same thing, because it is not of a and b is necessary. That means it is true in all possible worlds. So once again you apply, I will write it here, not of b, this branch closes. So now what is left is this one. Under this not b implies 1, again you need to write this one, not a is true in a world 2 and not b is true in a world 2. So now above that we have all these things, b is true in a world 2, a is true in a world 1. So now not b is true in a world 1 and b is true in a world 2. So a1 and this is a2, this branch remains open. Now not b2 and b2, this remains closed. So now we have this open branch. So that means if you take individually the possibility of a and possibility of b, it doesn't have to lead to b. So now if you are asked to construct a counter example, so let us check it again here. We have exhausted rule for, so b is true in a world 2, not b is true in a world 2. Now so here if you write like this, so now you check it here, that suppose if you apply the second rule here, it will become not a is true in a world 2, not b is true in a world 2. So b2 and not b2, this closes, and then this remains open, not a1, not b1. There is no way in which you can close the branch. So now what could be the counter example for this one? So now we need to see from the open branch. Open branch is like this. So what is true in a world 2? Not A, and not B is true in a world 1, and then B is true in a world 2, that is what we have written, and then A is true in a world 1, and it goes on like that. So now observe this formula. Now this is the relational structure. Of course you need to write it in a systematic manner. So that is like this. First you have set of words 0, 1 and 2. These are the possible words that we have, and accessibility relation is like this. 0 is accessible to 1, and then 0 is accessible to 2. This is the thing which we have. And V, valuation function is that given atomic sentences A, B, A is true here and B is true in a world 2. All these things are listed here. So that's why we have a complete Kripke structure. So now this could serve as your counter example. Now apply this one here. So now if you go to the original formula, this is going to be like this. Now possibility of A and possibility of B. So possibility of A is true and possibility of B is also true. So this makes this formula true. Now what about possibility of A and B? So now if you take the possibility of A and B, suppose if you go to this world where A is true but B is false, so that means this is going to be false. In the same way, although B is true here, A is false here, that makes A and B false. So now for that reason, so this is not going to be a theorem, and that is going to be the counter example. So let us consider some more examples so that we will understand this thing in somewhat better. So assuming that let us consider some more little bit of complex kind of examples, and they are here like this. So with this we will end this lecture. So imagine a situation that we have this thing. Now we are trying to construct S4 counter examples. So this is a little bit of difficult formula, and with this we will end this thing. Necessity of P implies Q. Necessity of P implies Q, or necessity of Q implies P. We need to be careful about the brackets. So this tells us that it's a disjunctive kind of formula. Necessity of P implies Q, that has to be the case, or necessity of Q implies P. So now how to go about it, whether it holds in S4 or not. This is a question mark that we are trying to start with. So now for this we need to negate the formula, that is the one with which we do. Then it is going to be like this. P implies Q, or not of Q implies P. So this is there is a disjunction here. Negation of disjunction is conjunction. So it is going to be like this. Negation of necessity of P implies Q. Now negation of necessity, and necessity of Q implies P. Necessity of this thing. So we need to be a little bit careful about the brackets. Now negation of necessity is this thing. It is possible that not, and then you need to push this negation here. So now this will become formula this one. Now if you further simplify it, it will become this thing. Negation of necessity will become possibility of not of P implies Q. The same thing we have simplified it by using modal negation rules. So this is done. Now coming back to second, negation of necessity is possibility, and you push this negation inside, then it will become, in the first step it will become like this. So we need to ensure that we should not write P for Q, Q for P, etc. Sometimes we will confuse ourselves and we write it in that way. We need to check it carefully. So now negation, you put this negation inside, then this will become negation. So we have this formula, x implies y, this is x and this is y. Negation of x implies y is x and not y. So that is, so x is q and not y is this thing, not p here. So this is the one which we have now. All these things are true in a world 0. Now what is that we are trying to check? We are trying to check whether this given formula holds in S4 or not. S4 already includes T rule already, but we don't have to use this T rule here. Let's see whether we can use it. So now possibility of not of P implies Q, and here you have possibility, necessity of Q, etc. Let us remove this possibility operator. Then you are already in 0, you are moving to a world 1, and in that world this whole sentence has to be true. It has to be true in the world P, and it has to be true in the world 1, because not necessity of Q and not P is written in this sense, one after another. Now coming back to this one. So the strategy here is that always you work on possibility operators and then you move on to necessity operators. If you understand one particular kind of problem, you will be able to solve all other kinds of problems easily. And you need to note that whenever you have your branch open, remains open, from that you need to construct a counter example. Counter example in the sense that your premises are true and the conclusion is false. Coming back to this one. This is the one which we need to see. Possibility of this one. So now once you remove first possibility, you are not supposed to go to the same world 1, but you have to go to a different world 2, and in that world possibility of not of P implies Q has to be true in a world 2. Now once again you apply this one. If you remove the possibility operator, then it's going to be like this. So I am writing it here. So if you remove the possibility operator here, and this will become so now right now you are in a world 2 and you need to go to another world 3, and in that world this P implies Q has to be true. This is the one which we need to use. Now we have a formula which says that necessity of Q is true in a world 1, but we don't have we don't have any way to go from 3 to 1. So now this can be further simplified into P3 and not Q3. So S4 requires that your accessibility relation has to be transitive, or it can be reflexive also. Reflexive transitive holds, then that system is called S4. Now so in this case a possibility of not of P implies Q which holds in 2, and now we have this thing. So the problem is that P is true in a world 3, but you have a formula not P is true in a world 1. You cannot close this one because a formula is true in one world, another formula is true in another world, and unfortunately there is no connection between 1 and 3, because we don't have such thing called 1 is accessible to T and then 2 is accessible to 3. Of course 2 is accessible to 3, but there is no way in which you have this thing. 0 is accessible to 1 and 0 is accessible to 2, but we don't have such kind of property that in 1 is also accessible to 2. In that sense we don't have this particular kind of thing, so that we can say 1 is accessible to 3. So now this will serve as counter example. So you need to invoke some other kinds of properties, like in this case for example, if 1 has to be accessible to this one, then we have seen Euclidean property, that is this thing, 0 is accessible to 1, 0 is also accessible to 2, then 1 is accessible to 2. So that is not available here. So we are not invoking Euclidean property. Equivalence relation involves reflexive, transitive and symmetric. Now the branch remains open like this. From the open branch you need to construct a counter example. So since we have taken 3 worlds into consideration, let us say this is 0, 1, 2, and even you have world 3 also. What is accessible to what you need to write. So 2 is accessible to, this is 3, 2 is accessible to 3. In that world your P is true and not Q is true. So now here in a world 1 not P is true in a world 1. So this will serve as your counter example. The only thing you need to do is you need to draw accessibility relation like this, but we don't have accessibility relation from we have accessibility relation from 0 to 2 also, 0 or 2. So, in this way this branch remains open and this will serve as the counter example. So, I will stop here. In the next class we will be talking about possible worlds and what is there is an important position in with respect to the possible worlds, and it is popular these days and it is highly debatable, and that position is called modal realism. Thank you.